Great, well thank you very much, and thank you for the invitation to come here. It's a great pleasure to be back in Taiwan after, I think, 11 years. It was the last time I was here. It's far too long. So thank you for the chance to come. So today I'm going to give you a whirlwind tour through some topics in both astrophysics and physics that we've been working on related to the clusters of galaxies. So let's start with the big picture. Let's see if this goes. The most basic thing we do as astronomers is try to understand how the universe came to be, how structure in the universe formed. And of course we have these beautiful simulations. This is the illustrious simulation, which is already quite old, showing how structure came to be. Now, in this talk, we're going to be focusing on galaxy clusters, and galaxy clusters have a special place in this cosmic web of structures. Galaxy clusters are the locations where these intergalactic filaments intersect, and you start to get mass flows down these filaments, and they build what are ultimately going to be the most massive gravitationally bound objects in the universe. That's galaxy clusters. In this beautiful simulation from Illustrious, you can already see that. Let's see. Here's the time scale down here. We're not even at redshift of 1 yet, and you're starting to get this amazing feedback physics happening. The process of galaxy building is starting to push back on itself. You have powerful energy injection from stellar winds, from supernovae, and especially from active galaxies. And that is actively fighting against galaxy formation and evolution in this simulations. And again, that is an environment where in clusters of galaxies that is writ large. That is the most dramatic examples of feedback that we'll be talking about in this talk happen in clusters of galaxies. So. Yeah, going backwards. Okay, here we go. So these are the topics that I'll be quickly going through. So there's basically three main topics I'm going to be talking about. One is the use of galaxy clusters to probe AGN feedback, the process of how supermassive black holes affect large-scale structures. And I'm going to argue that in galaxy clusters we have a chance to really look at that at a mechanistic level, trying to understand some of the physics that might be going on in the actual feedback process, which often in discussions of AGN physics, the AGN feedback, the physics part of it is brushed aside. And one of the particularly interesting areas, and the thing that I've been spending quite a bit of time on, is understanding the role that real plasma physics may have to play in this. I'll show you and hopefully convince you that there's some really interesting plasma physics at stake, in play. The kind of physics that gets me talking to colleagues who do fusion research, and that actually is relevant for the way that feedback happens in these clusters. The second topic is related to one of my favorite objects, supermassive black holes. Galaxy clusters, and especially the central galaxy we find in the center of galaxy clusters, are the location of the most massive supermassive black holes that we know about. The black holes that can exceed 10 billion solar masses. And so understanding the history of those black holes is important for understanding black holes in general. And in particular, I'm going to be talking about some new results on the spin of those black holes and what that might be telling us about the evolution of the black hole population. And then the third topic is something a little bit different, which is using galaxy clusters as a laboratory for doing some particle physics. And in particular, I'm going to argue that clusters are an ideal environment for looking for axions and axion-like particles. So I'll give you a very brief primer when the time comes to what axions are and why you might want to care about them, and how galaxy clusters are truly unique environments for looking for this particular aspect of particle physics. And then hopefully I'll have time at the very end to talk about the future and the thing that's the observational technique that binds this all together is X-ray astronomy, and in particular high resolution, high spatial resolution X-ray imaging and spectroscopy. And I'll hope to tell you about some of the future prospects for that field. Okay, so let's dive in. So galaxy clusters, I always like to think that they're actually very poorly named astrophysical objects. It is true that they are a big cluster of galaxies. So this is the Perseus cluster, and there's several hundred galaxies in this cluster. But in fact, the fact that they're a collection of galaxies is sort of not the main physics that's going on. Really, the dominant mass term here, the dominant object is a giant dark matter halo of order 10 to the 15 solar masses. And the galaxies are orbiting within that dark matter halo. But the galaxies are not even the dominant baryonic component. Most of the baryons, 80% of the baryons, reside in hot plasma that fills the space. It's in hydrostatic equilibrium in the gravitational potential of the dark matter. And I was talking earlier on. You stare at this X-ray image. This is from the Chandra X-ray telescope, the X-ray observatory of the Perseus cluster. And this actually matched. This is matched exactly in spatial coordinates. You have to really stare to even see the galaxies. Okay, the galaxies just don't appear in this X-ray map. So 80% of the baryons are in this atmosphere, in this hot plasma atmosphere. It's 40 million Kelvin in this case, and they basically don't care about the galaxies. Now, if you map out, these are some of the basic characteristics of these clusters. So it's about 10 to the 14 solar masses of this hot plasma, the hot intracluster medium, and these are some typical parameters for that hot intracluster medium. At this point, I want to point out two things. One is the mean free path of the particles in this plasma. 0.1 to 10 kiloparsecs. That is not small. Okay. I mean, it's the mean free path is smaller in the middle than it is outside because it's denser in the middle. But normally when you're thinking about gas physics, the mean free path is so small that you don't care about it. This is not small. This is galactic scale mean free paths, and that's going to come into play a little bit later. The other thing is that these clusters, when you map out their temperatures, which you can do with the Chandra X-ray Observatory or with XMEM, you find that there's a very strong depression of the temperature in the core parts of these clusters. And that is understood as the effect of radiative cooling. I mean, you are seeing the X-ray emission from the gas. That is cooling the gas. And that's why the center of the clusters are cooler. But then the question is, well, why doesn't that cooling run away? Why don't the centers of these clusters actually cool all the way down to molecular temperatures? And that is a very good question. There's got to be something stopping them from cooling down. The cooling timescales in central these clusters is only of order 100 million years. Okay, so on astrophysical timescales, they would cool down very quickly if they weren't being heated. What's heating them? The central active galaxy. So yeah.
So Chris, what's the dominant cooling?
Bremsstrahlung. It's just thermal Bremsstrahlung. Yeah. So if you go here, you see this image is structured. It's not just a featureless atmosphere. There's a lot of structure in this image. There's these bubbles and there's these. There's these. If you stare carefully, there are these edges, and so we interpret this as being the central jetted active galaxy is pumping energy into the intracluster medium. That is, driving various fluid modes, driving shock waves, driving cavities and sound waves, and that's what's heating the gas. So there are many examples of this now. I mean, the realization this is probably what's going on is at least 20 years old, probably a bit longer. And there's been many objects studied in detail. This is a particularly extreme example. The blue here is the X-ray image, and then the red is a radio image. And you can see that in the X-rays, there are these nice cavities here, and that is actually coincident with the radio, the radio jet. So the radio jet is clearly scouring out those cavities and probably pumping a lot of energy into those cavities. But just because you drive a jet into, just because you start stirring up the central parts of these atmospheres, doesn't mean you heat them. Just if you stir something up, that's not the same as heating it. So for a long time, the question has been, what are the actual mechanisms, what are the physical mechanisms by which energy is transferred from the AGN into the cluster gas? And at one level you can say, well, that's, you could understand the astrophysics without understanding that question. But if you want, for example, to understand how these processes scale as you go out to high redshift, and as the properties of the gas might be changing significantly, then this is actually an important question, what the actual physics is. And of course, understanding the physics is an important goal in its own right. So to sort of dig into this, what does a radio galaxy look like when it's interacting with intracluster medium or anything? Well, what the various structures, so classically the structures you set up are you drive a jet in some direction, the jet travels out, and then there's a termination shock the jet hits. So the jet hits the surrounding material, and that's a strong shock wave. So along the jet, if we go in, for example, into the here's a density map. It's a little bit hard to see, but there's a strong shock here. And then the jet backflows, and it creates what we call a cocoon. So the cocoon is this structure here, and that cocoon blows outwards sideways, and it drives a weak shock sideways. You can kind of see this maybe slight discontinuity here in the density map. That's a weak shock that's being driven out sideways. And then there's lots of other hydrodynamics that go on. You can see in this best seen in this map here, where we're sort of picking out energy fluxes, that you get lots of sound waves created in this structure. So those are some of the fluid modes you set up, and potentially those are some of the fluid modes that you might be trying to thermalize to actually offset the cooling. So some work that now a little while ago I did with Karen Yang, who I think is well known to many of you, while Karen was in Maryland, was to try to understand how this works in an actual, an idealized cluster setting, but still a cluster setting with a lot of the relevant physics going on. So we have an AGN, a jetted AGN at the middle. It's fed by cooling, so there's cooling that goes on in the gas, and that sends cold material in towards the center, and that feeds the AGN, and then you produce a jet and you blow you blow the jets out. And what you find is, lo and behold, this does actually achieve a regulated state, that you can actually achieve a long-term regulation where the energy injected by the jet is balancing the radiative cooling. Now that's nice, but the interesting thing is, and this was largely the point of the paper that we did with Karen, is that while you can set that up in these kind of nice simulations, in fact, none of the real physics is actually captured by these simulations. And when you go into the simulation and say, well, what is actually doing the heating here? Let me run that again. What's actually doing the heating here? What you find is there's two things doing the heating. One is that there's a mixing going on. You have the high entropy material coming down the jet, and ultimately, sort of out here, it's being mixed in with the low entropy material, with the atmosphere, and that's effectively heating the atmosphere. Okay. Problem is that in reality, radio galaxies actually look like this. This is a nice meerkat image of a radio galaxy, and the take-home message from this is that this is not just a gas that you're putting down these jets. You're putting relativistic plasma down the jets. There's clearly magnetic fields in this situation. You can see here that how the relativistic plasma, another word for that would be cosmic rays, are streaming along these field lines. And fundamentally, if you take a bunch of cosmic rays and you mix them in with gas, it's possible that you haven't actually done anything. There can be no energy transfer between the cosmic rays and the gas. So just because you mix this stuff in doesn't mean you heat the gas. And then the second thing is that when you drive the various, you saw in Karen's simulations, the various shocks and sound waves that were being driven out into the gas, well, that's another place you could dissipate. You send these waves out, and those waves could carry energy out and dissipate. And indeed, in real data, we see a lot of these structures. This is the Perseus cluster, where we've sort of stretched the image. We've subtracted a smooth background and stretched the image to bring out structures. And you can see a lot of ripples and things that may well look like series of weak shocks or acoustic waves. But of course, a sound wave can quite happily travel without dissipating. I mean, if sound waves dissipated, you wouldn't hear what I'm saying right now. So, so just having waves putting out is also not a be all and end all. So there's clearly a lot to understand about the microphysics of what's going on here. So, just to sort of again highlight some slightly older work that Karen and Mateusz Rakowski led. You can do models where you put a proper cosmic ray treatment or a more proper treatment of cosmic rays in, and actually look at the physics of how the cosmic rays and the gas interact, and that's what's done here from this paper in 2017. And you can start to see what physics you need to put in with the cosmic ray interactions to start to stabilize the clusters in a reasonable way. So that's the cosmic rays. But the direction that I've been interested in recently is trying to understand what's happening, not necessarily with the cosmic ray interaction, but what's happening out in the bulk of this cluster. I mean, we have to somehow heat this whole part of the cluster here to offset the rate of cooling. And I think of this as a fluid dynamics problem. Okay, there's actually no evidence there's strong cosmic ray heating out here. It's really a fluid dynamics problem that we're shaking this inner part of the cluster, and we have to understand how it gets heated. So we need a dissipation source. We need to understand the dissipation in this system. And this is where that large mean free path that I pointed out at the beginning comes in. This is not your textbook plasma. So therefore you can't use textbook viscosity or thermal conduction, for example, on this. So let me focus on thermal conduction. Sorry, let's come back to this plot here. Why thermal conduction? Well, thermal conduction is actually a very interesting piece of physics. So in its essence, thermal conduction will transport heat from hot to cold. Okay, that's easy. So why is it interesting? Well, firstly, we have a strong temperature gradient in these clusters. So you could imagine, maybe, that the AGN doesn't actually have to do very much. All you need to do is conduct heat from the hot part of the cluster out here into the cooler part of the cluster, and maybe that would help stabilize it, if conduction is powerful enough. The second thing is that thermal conduction is a source of dissipation for waves. If you have sound waves traveling through a medium that has thermal conduction in it, those sound waves will dissipate. So that's interesting for this. And the third thing is that we know that there are cold gas filaments in these clusters. I mean, truly cold, molecular gas filaments, and that may well be what's heating what's fueling the central AGN. You can actually trace those cold gas filaments falling inwards towards the AGN. So the process by which those cold gas filaments are condensing out of the hot medium, you've got to go from 40 million Kelvin to condense out down to molecular temperatures. It's a thermal instability, and thermal instabilities can be very strongly affected by thermal conduction. So there's a good reason to look at thermal conduction. So what's the physics of thermal conduction? Well, in classical theory, the so-called Spitzer conduction, thermal conduction is a diffusion process. It's actually described by a diffusion equation. You have a hot region. The energetic electrons in that region will be diffusing out towards the cooler regions. And you can modify it if there's a magnetic field present, because if there's a magnetic field present, then the electrons are actually gyrating around the field line, so they're channeled by the field line. So they won't diffuse sideways, but they'll diffuse along the field line. But, as I said, the mean free path in the intracluster medium is only 1 or 2 orders of magnitude below the typical temperature scale lengths. So that this temperature scale here is less than 100 kiloparsecs, and the mean free path is of order 1 kiloparsec. Yeah.
How do you estimate this?
Sorry.
How is this 10 kbc scale estimated?
Oh yeah. So that's estimated from classical. You do the classical calculation of what is the mean free path of a particle in a plasma that's undergoing Coulomb collisions. And that's how we know. So that calculation is classical. It's just the Coulomb scattering of the electron as it goes through the plasma. So does this affect anything? And of course, I wouldn't be here telling you unless it did. So I teamed up with my plasma physics colleagues at Maryland. Maryland has a very good plasma physics group that works a lot on solar plasmas and fusion plasmas. And we asked the following question: suppose we do a classical experiment in a PIC code, a particle in cell code, which is the simulation tool of choice for plasma physicists. We take a box of plasma and we simply put a hot plate at one end and a cold plate at the other end. And we have a magnetic field threading, a weak one, threading the problem, and we see what happens. And what you might have thought, and what the classical extension of Spitzer would say, is that there's simply free streaming, and in this case there's no collisions at all. It's a collisionless plasma. Spitzer would say there's a simple free streaming of electrons down the box from the hot to the cold. They're just unimpeded flow, stream of electrons through the box. And that's the so-called Carey-McKee theory. That's not what you find. What you find is this: boom, the box blows up in a bunch of waves. And when you look at the nature of these waves, they're what's called Whistler waves. So they are plasma waves. There's sort of electromagnetic waves in the plasma that have a very particular character. If you go into the rest frame, if you go into the frame of reference of the wave, there's simply a rotating magnetic field vector. And when you do the linear theory, it turns out there's an instability. There's an instability which can take the energy, the heat flux through the box. It can take that energy source of the heat flux through the box, and it can use it to drive these Whistler waves. So, and then what happens? These Whistler waves become scattering centers for electrons. So even in this system, which is completely collisionless, these are electron paths here. The electrons start to scatter around in the box. Okay, driven by this physics. But you can kind of see it's non-linear because it's the heat flux through the box that's driving these Whistler waves, and these Whistler waves are impacting the heat flux through the box. So there's some interesting things here. So in essence, to cut to the chase, in this completely collisionless case, which is of course not intracluster medium, what you find is that the heat flux is suppressed by this form is wrong. The heat flux is suppressed by a factor of beta, where beta is the ratio of the gas pressure to the magnetic pressure. So in galaxy clusters, that's 100. The magnetic pressure is 100 times weaker than the thermal pressure, and that's the factor by which you suppress conduction. So in these systems, it would suggest you can suppress conduction by that much. This just shows you a little bit deeper some of the results of those simulations. You can plot the heat flux through the box as a function of the plasma beta. So again, weak magnetic fields are over here, and strong magnetic fields are over here. And what you find is that once you get over some threshold in this quantity, then you have this proportionality of 1 over beta. If you're paying attention, you might suddenly think this is a bit strange, because the weaker the field is, the stronger this effect is. Okay, and that's because the stronger the suppression is, the weaker the field is. And the reason for that is that the magnetic field in this game is actually playing the role of an agent that's trying to stop these instabilities kicking in. Okay, the magnetic field is an agent that's actually trying to suppress this. So the weaker the field goes, the stronger these instabilities can be driven. It's these instabilities that are giving you the suppression of the heat flux. Then also the higher the beta you go, so real clusters at 100, the stronger these fluctuations become. There's fluctuations in the. So it's sort of to very recent work on this. What we did, and I will skip over all the details because there's probably a small number of people in the world that truly get excited about this kind of stuff. But you can take the lessons of these PIC codes and extract from it a collision operator that you can then use to construct a fluid description of this. So what that basically means is you can now take your favorite fluid dynamic code, or more precisely MHD code, and you can add extra terms that capture as accurately as possible the conclusions of the PIC code. And that's what we did in this paper that Jim Drake led in 2001 to go through that formal analysis of constructing those new fluid equations. And then the thing that we didn't realize at the time, but we've just realized recently, is that when you just calculate through the actual heat fluxes that are predicted from this when you're in a state of equilibrium, they look like this. So what this plot is here is on the x-axis we've got the temperature gradient in the plasma. Okay, so strong temperature gradients are on the right, weak temperature gradients on the left. And then on the y-axis you've got the heat flux. And so as you start increasing temperature gradient, it's just linear. That's Spitzer conductivity. And then you reach a threshold where this new Whistler physics kicks in, and it actually does kick in at a threshold condition. And when it kicks in hard. And it kicks in, and you actually get a suppression of conduction of the conductive heat flux for a while. So this is really interesting because when, as a fluid dynamicist, you look at this, you can suddenly start seeing the prospect for instabilities occurring. Yeah.
I want to clarify something.
Yeah.
A similar configuration that was the cluster with the plasma with the initial temperature gradients.
Yes.
Actually, Weber-like instability could also prevent from this heat. Use heat conduction. Is this also similar to the
in the simulation?
Or at least some analytic calculation. In your simulation,
yeah. So in the simulation, we have a hot plate here, which is a source of Maxwellian particles with certain temperature, and a cold plate here, which is the source. And in fact, in the initial condition, the best posed initial condition actually is one where you then have in the initial state a uniform mixture of those two Maxwellians through the whole system, and then sort of quite quickly it locally starts creating a Maxwellian with a temperature change that happens. So in these PIC codes, you really are modeling, of course, the full velocity distribution of the particles. You can characterize that as a temperature and the temperature gradients, but that's what we do. Yeah. So there's a prospect for instability here. So let me sort of cut to, for the sake of time. One consequence of these kind of negative responses here means that if you increase the temperature gradient, your heat flux goes down. Okay, and that means that you might destabilize sound waves. So in normal situation, you have a sound wave like this. So this is temperature along the wave. If you have conduction, the conduction tries to carry the heat, tries to smooth the wave out. It's taking the hot peaks and trying to smooth them out, and that damps the wave down. If you have a background temperature gradient, you've just got heat flux going down. If you now put a wave on here, and you say that when the wave is steeper, when the temperature gradient is steeper, the heat flux is less, you can kind of see here that here you've got high heat flux, there are low heat flux. You're going to pile heat up at this point. And vice versa, here you have a high heat flux, here you've got low, you're going to take heat away from this point. You're going to make this wave stronger. So there's an instability that comes in there. And the paper in progress is the linear theory of that. So if you go to a real cluster like Perseus, it's abound with interesting structures that have no explanations. And one of them is this feathering structure you kind of see through the image, which unfortunately they've drawn big bright white lines all over, which hides it. But there is actually there's a feathering structure in this cluster, and I postulate that might be this instability that we're seeing. Okay. Moving on, so that's the cluster physics. Let's now go right into the center and look at the black hole. So in the center of these cluster galaxies, we have what's called the brightest cluster galaxy, the BCG. And the BCGs contain the most massive black hole, supermassive black holes in the universe. This is a classic compilation of black hole masses versus velocity dispersions for galaxies. The BCGs, the central galaxy, the galaxy central cluster central galaxies, are the ones up here. Okay, they're the most massive black holes. These are also the AGN that, of course, lie at the heart of the feedback loop I was just telling you about, so that they're particularly interesting from that point of view. They were actually surprisingly poorly studied, not studied, they're studied very well, but surprisingly poorly understood, especially in their X-ray properties. And there's a very practical reason for that. It's easy to state and it's annoying to solve. If you look at the Perseus cluster, there's see that little black dot there? That little black dot is the location of an incredibly bright AGN, and it's black because the detector has saturated. Because Chandra has this exquisite point spread function, but it means that if you have a very bright object, it very rapidly saturates. Technically it's called photon pile-up. You pile photons into the pixel faster than you can read the pixel out. The problem is that if you now try and use another telescope that doesn't have this problem, which necessarily blurs the image out over a much larger area, say the XMM Newton telescope, you start mixing in all this bright intracluster medium. So you get a confused spectrum. So you've got the choice of having a saturated spectrum or a confused spectrum, unless you do something clever. And what are you missing in doing that? What you're missing is, a particularly key piece of physics that you're missing when you can't study the X-ray spectrum well is the reflection spectrum of the AGN. So down in the center we have the black hole in the secretion disk, and we know generically that AGN are powerful X-ray sources. Those X-rays we come from the corona. It's just a name for whatever produces the X-rays. But this is, it's got some kind of geometry like this. And we know that in many objects, that X-ray corona is irradiating the surface layers of the disk and producing reprocessing signatures that we can see, producing what we call the reflection spectrum. And this is one particular example of the reflection spectrum in an AGN Arcarian 564. So look at this plot here. What you're seeing here is the spectrum ratioed against some fiducial power law, and you can see this broad emission line here. This broad emission line is the emission line of iron from this accretion disk. So the spectrum of the disk, when you irradiate it, produces this strong emission line of iron. It's a fluorescence line of iron. And then because you're down close to a black hole where there are very strong Doppler shifts and very strong gravitational redshifts, that line gets broadened and it gets skewed. And it gets broadened and skewed into this. Now what you can do, which is particularly exciting, is if you have good data on a line like this, you can model it in great detail. And you can ask, how broad is that line really? And you could ask, well, therefore, how close to the black hole is the accretion disk getting? The closer the accretion disk is getting, the broader that line is. So you can measure a distance of how close you're getting. And then you appeal to standard accretion disk theory, and you say, well, what do you expect that distance to be? Well, you expect that distance to be what's called the innermost stable circular orbit. So general relativity tells you that the disk should orbit down, relatively well-behaved circular orbits, until you reach a critical radius inside of which orbits are unstable, just because of the relativistic potential. The orbits are unstable. And that relativistic potential is a function of the spin of the black hole. So if you look at this plot, this is plotting the radius of that innermost stable circular orbit in units of gravitational radii versus the spin of the black hole, all the way from rapidly retrograde spins through zero spins through rapidly prograde spins. So the more rapidly the black hole is spinning in the prograde direction, the closer the accretion disk can get in, and therefore the broader these reflection features can be. So this is a way you can measure black hole spin. This is a technique you can use to measure black hole spin. So can we apply this to clusters of galaxies? Well, there's one object we've found where we can do this. And this is it. It's H1821 plus 643. This is a wonderful object, so we should have a better name for it. But it doesn't look very impressive, but it's at a redshift of 0.3. So it's actually 20 times more distant than Perseus. And why is it a wonderful object? Well, it's a massive cluster. So it's a very rich cluster, but it has an extremely bright quasar in the middle of it. And that's a very rare thing. For clusters of galaxies to have a genuinely powerful quasar in the center is very rare. So it's got a 10 to the 47 erg per second quasar sitting in the middle of it. Got optically bright, classical optically bright, X-ray bright quasar sitting in the middle of this cluster of galaxies. Just to give you something which blows me away, gives you a sense of how powerful it is. This quasar sitting in the middle of this cluster, the Compton cooling of the quasar light on the hot gas dominates all other processes out to at least 5 kiloparsecs, and maybe further. Okay, so this quasar is having, an impact on the energetics and the ionization state and everything of the entire inner parts of this cluster. What you can do, though, is you can get decent spectra of this object with Chandra, and this is some work that my student, or my former student, Julia Reynolds did recently, and you can see there that emission line. Okay, so this is traced out. That's that broad emission line of iron. And you can start to model this, and I won't labor all the modeling details. The modeling process, there's a lot of parameters, because it's not just the spin of the black hole. You've got to worry about the inclination angle of the accretion disk, about ionization structure of the disk. You've got to worry about the other AGN parameters, the temperature of the corona of the AGN. So a lot of those things you've got to model. When you do all of that, you can come up with a posterior probability for the spin of that black hole, and that's what Julia found. Is this posterior here? Now it looks like it's kind of skewed towards high spins, but when you actually look at this, the peak of it is round about 0.6 or so. And let's now put that into context with all the other results from the community on black hole spins, which are collected on this plot. The vast majority of black holes which have been studied, which are much less massive than this one, are all rapidly spinning, which is interesting in its own right. Okay. When you get more, above say 30 million solar masses, the previous data had hinted that you started to pick up a tail of more modestly spinning black holes. And this object, which is now sitting out well above 1 billion solar masses, is very strongly confirming that. So what does that mean? Well, that's telling us something about the way these black holes grow. And when the nowadays, in for example these illustrious TNG and some of these other cosmological simulations, they're starting to trace black hole spin as one of the parameters. And what they find is that these low mass black holes are very easily spun up. The accretion always, even modest accretion events can rapidly tilt the black hole to be aligned with them, and then spin the black hole up in that direction. And then a new accretion event comes in, it tilts the black hole and then spins the black hole up. The more massive black holes, you can't spin them around like that, and there's a lot of mergers that come into play. The massive galaxies and the massive black holes, mergers are very important. So in some very recent work, you can see, this is just this year, you can see how in these theoretical models, it's the dots here are the theoretical models, they're color-coded by how many mergers these objects have gone through. And this would suggest that our object out here has gone through several mergers, if not many mergers, to get to the intermediate spin. So there's a lot of promise as we start to look at these techniques for probing out to look at the evolution of black holes. This is our low redshift sample. If we could imagine starting to do black hole spin at higher redshifts and doing redshift cuts, then that would be a powerful way. And maybe I'll tell you a little bit later how to do that. Okay, the final topic I want to get to, which is the how we use clusters for new physics, is I'm going to tell you about something I haven't mentioned yet for clusters. This is our list of typical cluster properties. They're magnetized. Okay, so your typical cluster has a magnetic field in it of a few milligauss. Sorry, a few microgauss. Doesn't sound a lot, but it's that gives you this plasma beta of 100. It gives you a magnetic pressure that's about 1% of the thermal pressure. The important thing is, though, that you have this plasma that's magnetized at a few microgauss on megaparsec scales. The total size of this object is of order megaparsec. So it's a huge system. It's a huge magnetized system. Now, this is ideal for people who study axions. Now, what are, because as I'll tell you in a second, the way you find axions, or the way you search for axions, is you pass photons through very long magnetic fields, very strong and long magnetic field path lengths. And so what are axions? I could give a whole colloquium on this, but I considered it, but I thought some of the other stuff would be more interesting. The history of it, axions were first proposed in the 70s to solve a particular particle physics problem, something called the strong CP problem. There's a particular, the strong force, the strong nuclear force, obeys a symmetry, so-called CP symmetry, that there's no reason why it should obey, in the fundamental theory. And I won't go through the details of why, but if you postulate the existence of a new field in the standard model, and there's a new particle that comes along with that solves this problem. So that's the original axion. Now, since then, it's been realized that this type of particle might be very generic in various extensions of the standard model. So, for example, in string theory, the extra fields you put in that give you these kind of particles, there's many of them. And so people could talk axion-like particles to distinguish it from the original particle that was proposed to solve the CP problem. Why are they interesting? They're interesting because the first thing that's not up there is they're actually probably one of the best motivated extensions of the standard model. I mean, as particle physicists, you take the standard model and you make hypotheses of how you might extend it, and some of those are better motivated than others. This is a well-motivated one. If we find them, this is a strong indicator of the direction to go in to understand the standard model. They're a very plausible dark matter candidate. And they're also a very plausible dark energy candidate, because there's a huge range of possible masses that they're allowed to have. If they have, and they may be very light, if axions have a mass of 10 to the minus 22 eV, okay, then they produce what's called fuzzy dark matter. This is dark matter where the Compton wavelength of the particle is now galaxy scale. So when you start to this is a large scale structure formation simulation, you start to have these filaments of dark matter, but you start to get quantum interference in the filaments because of the particles. Okay, but that's for 10 to the minus 22 eV. If instead you make the particle 10 to the minus 30 eV, then the Compton wavelength of the particle is now larger than the cosmic horizon. And in fact, if you put that into the Friedmann equations, it actually behaves like a dark energy. It actually accelerates the universe up. So they're kind of wonderful, magical particles. They solve everything. So how do we look for them? Well, the way to look for an axion, and there are many experiments based upon this technique, is you take a photon and you pass it through a magnetic field, and standard theory tells you that nothing should happen. I mean, we all know that photons passing through a weak magnetic field, nothing happens. But if axions exist, then as the photon passes through the magnetic field, in fact, it can actually interchange with an axion state. It's sort of very similar mathematics to neutrino oscillations. That if you have a neutrino, say the electron neutrino traveling along, it can undergo an oscillation into a muon neutrino, then back into an electron neutrino. So it's actually very similar to that. And that's it. There's many. I won't labor them, but there's many laboratory experiments set out like this. For example, you might have your photons passing through a magnetic field, and then put a brick wall in place, and on the other side have a magnetic field with a sensitive detector, and you see, well, has anything got through the wall when it shouldn't have got through the wall? You know, that's the kind of experiment that you can do. Now, if we take the theory of this and we start to figure out, you know, the propagation of these axions, and James Matthews, who was is a postdoc fellow in my group in Cambridge while I was there, he built a nice axion propagation code, just sort of solving the equations for axion propagation, which is on GitHub. It's called Alpro. If you do the axion propagation problem for a particular choice of axion parameters, a mass of this and a coupling constant of this, with cluster-like properties, so 100 kiloparsec length scale, 10 microgauss properties, and you ask what's the probability that a photon doesn't make it through the box, it looks like this as a function of energy. So going all the way from low energy to high energy, it starts to undergo oscillation, then there's a big drop there. This is the classical X-ray band. Okay, so we find that in the classical X-ray band, for these cluster-like parameters, we start to get oscillations in the photon survival. I need to go back here because this is important. All of these theories have a coupling constant associated with them. You know, so there's the axion has a certain mass, but there's also a number that tells you how strongly it's coupled to the electromagnetic field. And you know, there's enormous amounts of effort in the physics community to constrain that number, put limits on that number. So what we do is this. I call it the X-ray transparency experiment for clusters. We look at a central AGN, and we simply look at its spectrum. And as the X-rays from the AGN are propagating out, and of course X-rays are the part of the spectrum to do it in on the basis of the previous plot. If axions exist, at certain energies they should be cut out of that spectrum. So the spectrum should be distorted. And these are some example calculations when you're going through a turbulent magnetic field, not a uniform magnetic field, of what some of those distortions might look like. So the spectrum should be distorted as you get to the satellite. If you see distortions, then you try your best to model them, and maybe you've got the detection. If you don't see distortions, you can set a limit on the properties of the axions. So this is what we did. Keep an eye on the time. When did we start? It's
20 past 2.
Yeah. Okay. So yeah, no problem. This is how I actually solved the problem of saturation in Chandra. Is I used the diffraction gratings. So Chandra has diffraction gratings. You drop the diffraction gratings in, which initially seems like a crazy idea when you have a big diffuse cluster. But what happens is you take the bright AGN light and you disperse it out here. And it's very easy to go in and separate out that AGN light and get a nice pure AGN spectrum. The downside is the diffraction gratings are not very sensitive. I mean, meaning like the collecting area of them literally is something like that. Okay, so you've got to look for a very long time. This is 500,000 seconds. Well, not this particular plot, but the total spectrum I'm going to show you is 500,000 seconds. So this is the spectrum we got of the AGN in the center of the Perseus cluster, NC 1275. Nice, beautiful power law with no evidence of any distortions in it. Maybe there's a distortion here. That's at 6.5 kV. Well, we understand that. That's the iron line thing I was just telling you about before. But otherwise, there's some undulations here that are entirely consistent with calibration, with the kind of level of calibration that you expect. Same thing for H1821. Nice, pure power law going through, maybe some iron line structure, but no distortions here. So when you go through the modeling process and you you go through a process of making lots and lots of realizations of these axion distortions, treating the magnetic field structure as a nuisance parameter, because you got to average over many realizations of the magnetic field structure. You can make a constraint plot, and this is the current axion constraint plot that is actually curated, I think, at Michigan, and we've appeared on it recently. So this is the coupling constant here, and this is the axion mass. And the most competitive constraints for low axion masses are these cluster observations down here. Now, why is this particularly interesting? Well, string theory, to the extent it predicts axions, generically predicts low mass axions. So this is the range where we're interested in for string theory. And more interestingly, after we started publishing these limits, the string theorists got excited and started making plots like this, because string theorists can actually do toy calculations. They can do toy model calculations of reduced string theories and predict what kind of coupling constants you should be seeing out of their models. And if you look at the histograms to look at, so this is coupling constant on the x-axis, you can see that some of their predictions are already exceeding where we are. So we're already starting to squeeze some of the predictions of string theory. Now, it's very flexible, but it means that as we get better in pushing these limits down, it's not a crazy thing to imagine we might start seeing something interesting. So it's worth looking. It's worth looking. Okay, in the last 5 minutes, I just want to tell you about what next on this. Well, much of my last couple of years has been focused on thinking about what the next observatory should be that we'll do this with. And so a group of us have been formulating and pursuing the Advanced X-ray Imaging Satellite, which is a proposal for essentially a next generation Chandra X-ray observatory. And my deputy PI is Erin Kara at MIT, and I should also give a lot of credit to Professor Richard Mashotsky, who's at Maryland, who was the PI of this concept up until in the pre-decadal survey point. He shepherded the early stage of this project through. So to put it into context, this telescope, this plot here shows the point spread function that we have. So we're basically just a tiny bit worse than 1 arc second, but across a large field of view. Okay, so we have this exquisite imaging ability across a large field of view. Chandra is a little bit better than us, right on axis, but very quickly aberrates as you go away. So the Chandra is not particularly good for large area surveys or for looking at large objects. We have, depending upon the precise energies, we're considering 5 to 10 times the collecting area of Chandra. So you put that all together, we're a very powerful survey instrument and a very powerful instrument for doing, for example, cluster studies. This is the obligatory cartoon of the observatory. It looks like every other X-ray observatory, but it becomes your baby, so you like to show it. The key innovation here is the X-ray mirror. It's a new technology that we're using for the X-ray mirror, which I'll show you. No, I won't show you that. If you're interested in the X-ray mirror, I can just ask me questions about how we do that. So the science case for AXIS is very broad, and we've pulled together a great science team to pursue this. This is just the team leadership. In total, the team's about 30 people. And we have working groups looking at AGN, looking at compact objects and supernova remnants, galactic feedback processes, stars and exoplanets. There actually are implications of this observatory for exoplanets, because we can make very exquisite measurements of stellar activity. So to the extent that the host star has any bearing on the exoplanet, we can tell you about the host star. And then importantly, time domain astronomy. So lying behind all this stuff, that's a simulation of one of our deep fields. Now, deep fields in one deep field, about sort of a little bit smaller than the area of the moon, we'll detect about 10,000 sources, and about half of those will be AGN, including AGN going out to a redshift of 10. So AGN which are right at the point where Webb is just starting to see hints of AGN. In addition to that, we have spectra. So because the X-ray CCDs can get spectra, so this is some examples of what a cluster would look like, an obscured black hole and a spinning black hole. And then coming to the cluster problem, to sort of put it into context with Chandra, what I've done here is taken the Perseus cluster and broken it into tiles where you've got enough photons you could actually do some real spectroscopy with. These tiles where you've got, I think, 2,000 photons in a tile, you could actually do some real meaningful detailed spectroscopy. And just because Chandra's a small telescope, you're limited in that. With us, you can see that you can really get into the details there. And I know there are people here interested in galaxies, so we also have an important bearing on stellar feedback in galaxies. So this is a simulation of M33, and we can go in there and really start to see the individual star clusters, massive star clusters, measure their X-ray luminosity, get an idea of the energetics of those star clusters and the energy output, having their interactions with the surrounding galaxy. So you can really start in nearby galaxies to pull apart how stellar feedback is happening in a very detailed mechanistic way. And then the final case, which let me just sort of come back to here, is you can see that there's this tiny little divot on the side there. That is a on-demand antenna, which means that we can ping axis and repoint it on demand, and if we have a trigger sent to us from, say, Gravitational Wave Observatory, we can get on target in a good scenario in less than an hour. Equally well, we have an onboard transient detector. So if anything in our field of view, if we're staring like this and anything flashes at us while we're looking, we can immediately detect it, we can communicate down to the ground and send out the alert. So it's a very powerful observatory. So just the programmatics of that, this is a probe concept in proposal. The step 1 proposals are currently under evaluation. The rumor was that the selection meeting, like the final selection meeting at NASA headquarters, was Monday. So I am by my phone all the time. It's in my back pocket right now. These are big projects. So the budget for these is $1 billion in FY23 money. So it's getting more all the time. And we are told that this had better launched by July 2032. The idea, the logic that NASA is putting in place here is that because so much investment is being put into the Habitable Worlds Observatory, which is this monster project that's going to be, one of the ultimate telescopes from the infrared through to the ultraviolet part of the spectrum, but tremendously expensive, flying in 2040s, flying 2045. In order to bring balance to the field, these projects, which are by mandate, they're not in that part of the wave spectrum, had to fly quickly to bring balance. Okay, let me wrap up. So hopefully I've convinced you clusters of galaxies are great things to look at for a number of reasons. The interesting plasma physics for a start. It's a good place to look at feedback and the most massive black holes, and then also there's this interesting particle physics. This interesting facet of particle physics they're particularly well suited to do. So lots to keep us all busy, and I think at least right now I'm very excited about the prospects for the future of this, especially observationally. So let me stop there. Thank you.
So I have a question about the black hole spin. I think, so Oftentimes, in fact, for both models, we assume radiation efficiency like 0.1, which is like virtually low spin
Yeah.
holes. We actually don't actually have a good idea about this. So, based on these observations, at least in the local universe, can we start saying anything about this right now?
It's a good idea. It's a good question. Go back to this plot. So, I mean, these objects here, which are spin rates of 0.9 or more. I mean, this would be efficiency up 20% or so. So it'd be a much higher efficiencies. One way to observationally get a handle on the average spin of the supermassive black hole accretion is through the so-called Zoltan argument, where you count up all the black holes that you see, you count up all the quasar light you see, and then you basically ratio them, and that gives you the efficiency. And historically, attempts to do that have suggested quite high efficiencies, more than 10%, 15% or so. But every time that is actually a vulnerable technique, because every time you discover a new population of AGN that were hidden to us before, then your mass budget changes. So, for example, the whole discussion on little red dots right now with JWST could well be starting to shift the Zoltan arguments again. So I think it's all very much in flux, but it's a really great question. Yeah.
Same thought. But, I suppose that based on what you mentioned, that your spectral resolution makes significant change on the measurement. Actually, it's a broad line, so I'm not sure. But does GRISM start observation? This number of data points increases?
That's a great question. So it depends. The lines themselves are broad, so GRISM doesn't really make impact. But in many sources, they are potentially confused by lots of narrow lines. So imagine this spectrum. I mean, this is a particularly clean one, but in some AGN, there are strong narrow components. There are strong absorption components, narrow absorption components. And in a low resolution detector, you start to blend those in with the broad feature. So I think GRISM will actually have an impact on this, not so much in modeling the broad lines as such, but getting rid of all that confusion that we see. So I hope that we'll see many of the observations that are previously looked at sort of clean up a bit, and maybe some of the results will change. Yeah.
So I have a question about the first part where you showed the temperature profile versus cluster, and that temperature gradient looks like inverse proportional to the density gradient.
Yeah.
Is that a coincidence, or is
it's a great question. I was really taken by that when I saw it, and spent a long time. In fact, I had long discussions with Steve Balbus once about whether we could make a nice model where there was this gradient drove turbulence that was a source of that was a source of transport for these metals. That never really worked. So right now I kind of take this as coincidence that's where it is. But it's a really great question. There's clearly, there's this factor of a few radii in the cluster where there's a lot happening, a lot of different things happening.
Does this happen not only to Perseus but also other clusters?
Yeah, it's quite common. I mean, one thing that is true is that, again, looked at as a hydrodynamic system, this temperature gradient here makes it a very strongly stratified system. So it means that it actually takes a lot of energy to lift something up. So it sort of makes sense that the high metal, the metals that are produced in the central galaxy, are confined inside of that region. But why? So maybe that's all there is to it. But yeah, it's a good group.
For non-cool core, does the metallicity gradient also the step is still there? Or?
That's a good question. I actually don't know. I'll get back to you on that. But it's of course non-cool core don't have the cool core, but whether they have this, I think it's more dispersed, the metals. Yeah.
About the ion K alpha line.
Yeah.
I wonder if the line profile strongly depends on the position of the continuum source.
Yeah, that's a good question. So,
how do you constrain the position of the illuminator?
yeah, this is a good question. I think the literature has become too confused on this point, and for this reason. The models that we fit now, typically we're modeling it as something like a lamppost here, and the parameter that we're modeling is the height.
Yes,
it's the free parameter.
However,
But in
if we can constrain the position such as the shocks in the accretion flow
Yeah.
or from the jet launching region or something like that, then it will strongly constrain the parameter.
Well, maybe. What I was going to say though is that in fact, if you can take a very empirical approach to this, because in fact the actual geometry of the corona doesn't matter. What matters is the irradiation profile across the disk. You know, it's the energy flux, the impinging energy flux as a function of radius. That's what matters. And you can choose to model that purely empirically. You can just put a function down and say, my reflection off the disk is given by some function with some fitting parameters. And in terms of the reflection modeling, that's all you need. Now, yes, you know, a particular coronal geometry would imply a particular function, but you don't actually need to do that step. You can make an analysis thread that is completely agnostic to the geometry of the corona, which I actually think is a better approach because it's less fraught with biases and gives you essentially the similar results to the ones that I pointed out. I think that in the literature, the fact that we don't really know where the corona is, and the fact, for example, that polarization results with IXB are arguing against this kind of geometry now, that has been used as an argument against the spin modeling. But the spin modeling can be done in a way that's completely agnostic to the coronal geometry.
We fully know the accretion solution because it's a core standard disk.
Yeah.
So the only remaining parameter to theoretical constraint is just continuum source.
Yeah, I mean the disk is it's the internal structure of the disk in this technique actually doesn't matter. The disk is just a reflector. As long as we know the velocity structure, the disk is just a cold reflector. That's all and then we irradiate it. And what we need to know is what the radial function that we're irradiating it with is. Yeah.
Thank you.
Well, we're a bit out of time.